As this year's COSM reflects, we live in a very complicated world. One where technology such as AI and data centers, Web 3.0 and overarching questions surrounding superintelligence cause in us deep questions about machines versus humans, knowledge versus insight, determinism versus the creative pursuit of the deepest questions. This sounds like a daunting set of questions at first, but at the same time it affords us a unique opportunity to shape the direction of what George has called the new American century. One where human creativity is at the center of insight and abundance. Make no mistake, there are a myriad of decisions we can and will make personally, as a society and as a culture, that will determine the outcomes here, and the guardrails we decide on will either unleash an explosion of human creativity as we've never seen before, or we will abdicate to the powers that be who want to make those decisions for us. I, for one, welcome the opportunity to shape this conversation and to put creativity at the core of the new American century. To help us frame this, I'm going to introduce our main speaker, Gabriel Rene. Gabriel is the founder and CEO of Versus, a next-generation cognitive computing company developing an operating system called COSM, ironically, K-O-S-M, the world's first AI OS for the development and deployment of AI-powered applications. Gabriel is a longtime technologist and has been at the intersection of AI and IoT, XR and Web 3.0 and spatial technologies for many decades. He's the author of the #1 international bestseller, The Spatial Web, How Web 3.0 Connects Humans, Machines, and AI to Transform the World. He's specifically focused these days on developing standards for the ethical interoperability between AI and other distributed computing technologies. So with that, I'm going to ask Gabriel to join us. He is joining us via Zoom, I believe from LA. And there's Gabriel Rene. So please join me in welcoming Gabriel.
Hello, everybody. Great to be here. Thank you for this opportunity to share a little bit about the work we're doing at Versus. My name's Gabriel Rene. I'm the CEO of Versus AI. I'm also the executive director of the Spatial Web Foundation. And today I want to paint for you a picture about the future of agents. Over the last 2 years, we've seen this explosion around the narrative of artificial intelligence. Jeff Bezos describing this as the key technology that will in fact be disrupting every industry. I think that every once in a while, you have a foundational technology that's not just another mousetrap that acts as a new disruption layer for the next 1,000 disruptions. And artificial intelligence has certainly promised to be that. But today I want to share with you how the work that we're doing at Versus, along with a handful of our other colleagues, is actually disrupting AI. Where is everyone going with AI? The main theme has emerged around autonomous agents. Autonomous agents can be thought of as the ability for a software-based agent to be able to make its own decisions and take actions in an environment without any human control. In fact, often when we use the term AI, we tend to think of it through the lens of artificial intelligence. I'm going to talk about why that's a bit problematic today, but the word that we really should be thinking about is autonomy. Autonomous intelligence of a whole new kind, and how this is embodied in software with software systems that can take their own actions and make their own decisions. Why do we want this? Because humans have effectively reached a sort of limit on our cognitive abilities. The size and scale of the challenges that we face today at planning scale and beyond are difficult for us. And in the past, whenever we reach the boundaries of our biological limitations, we invent a new tool, whether that's a spear to be able to grab some food just beyond our reach, or rockets that can move us to other planets, telescopes and microscopes that let us see deeper or further. But the cognitive function, not just memory, not just libraries and books and the web, or even, I would argue, today's AI, but the ability to have systems that can think and figure out challenges beyond what we can to solve the problems that we can't, is the key, right? We need something to help us manage the sort of exponential complexity of the modern world. And this is what we want agents to go beyond human intelligence. So we want agents to be able to perform at the speed and scale and power of computing systems, but be able to understand the complexity and the uncertainty and the dynamics of real world, real-time situations. It's critically important if they're going to be autonomous that they're trustworthy, right? This means that they must be accurate and they must be able to adapt to circumstances as they change. They're going to need to be able to make sense of information when there aren't a million examples, when it's ambiguous, when it's fuzzy, when it's uncertain, and still be explainable enough to be trustworthy for us to grant their autonomy. And they're going to need to be able to collaborate at scale. Agents are not just employees. They're going to be embedded into IoT devices and robots and cars and drones and toys, in our electrical, dynamic electrical grids and our supply chain. So they have to be able to collaborate, share knowledge, skills, insights, and do this at the speed and scale that can solve some of these exponential challenges and opportunities we face. And everyone is pivoting their companies around this. Even just in the last few days, Satya coming out, their latest version of Copilot, saying agents are the new apps for an AI-powered world. Bill Gates saying agents are not only going to change how everyone interacts with computers, they're also going to upend the software industry. And essentially, they'll be autonomously developing solutions in real time, much like we rely on humans, not to just have a packaged solution or application, but to figure things out as you go. This is going to upend the software industry, bringing about the biggest revolution in computing since we went from typing commands to tapping on icons, hinting at sort of natural ways of interacting with these agents. And Mark Benioff from Salesforce is that we have to pivot the whole company to agents, just as we did data and the cloud before that. Jan LeCun is widely considered one of the top scientists in the world, one of the early developers of artificial intelligence technology, and he is the chief scientist at Meta. And he has pointed out that LLMs have some fundamental limitations that do not set it up well to be the kind of foundation that we would want for agents. And he talks about these as the four capabilities necessary for human level intelligence that LLMs do not exhibit. Essentially, the ability to have a memory, the ability to understand the physical world, the ability to reasoning and planning. And this term reasoning has become the sort of key essential phrase and the capability set that all of the companies are saying is required. You need an agent to be able to figure out what to do if they're going to autonomously act and do it effectively. And we just saw OpenAI do their latest raise at 160 billion plus and laid out their vision for where the organization was going. The kind of key piece that you need to get to agents all the way at the end there is reasoning. And this is the vision that they've laid out. Level 1 chatbots, level 2 reasoners, human level problem solving in order to get to agents and then beyond. Why? Because again, if you're going to have agency, if you're going to have autonomy, you're going to execute decisions and actions by yourself, we have to be sure that you're making sense of the world. So you have to be able to reason. When they rolled out their latest version of ChatGPT called O1, this is just a couple months ago, despite billions of dollars being spent around attempting to achieve higher levels of accuracy and hoping for common sense reasoning in these systems, we see these same sort of hallucinations and errors that persist. And today I'm going to explain to you why those exist and why these are an unsolvable problem for the kinds of critical real world activities that we want agents to do. And so, I saw Sam post this. He said, here's O1, a series of our most capable and aligned models yet. O1 is still flawed, still limited, and still seems more impressive on first use than it does after you spend more time with it. And I couldn't help but try to imagine Steve Jobs or any CEO of any technology company in the last 35 years walking out and introducing the latest project by saying, here's the iPhone. It's still flawed, still limited, and still seems more impressive on first use than it does after you spend more time with it. Perhaps we could think of this as refreshingly honest, but the reality is that these systems are deeply flawed in ways that we can't trust. They are what we call, unreliably unreliable. It's because they throw errors that no common sense person that understands how the world works would come up with. And so the story of the last, I think, the sort of buried lead of the moment is that Apple was going to invest in OpenAI. And we found out on September 27th that they bailed out. On October 2nd, OpenAI closed their multi-billion-dollar round. And on this October 7th, this month, just about 3 weeks ago, 5 days after OpenAI closed their round, they released this paper. And I want you to think of this as the emperor wears no clothes moment. And I believe this is indicative of why Apple decided not to invest either in OpenAI or really in a future based on LLMs. So this paper is created all researchers from Apple, and essentially is called the GSM 8K test. That's grade school math, and there's about 8,000 questions. What they're trying to figure out is, can large language models do reasoning? You can see here at the bottom that current LLMs are not capable of genuine logical reasoning. They're doing pattern matching, but they're not doing reasoning. I think this is the moment where O1, which was supposed to be considered this reasoner, which is supposed to get us to agents, which was codenamed Strawberry for a long time. I like to think of this as the apple has just squashed the strawberry. And I'm going to walk you through just a couple of things. There's a Wired article that came out about a week ago that does a great job of sort of exposing this and walking through it, very readable. And there's the paper itself. But here's just a couple simple things. And I want you to stop thinking about AI through the lens of some sort of super intelligent alien intelligence. I want you to be very discerning in how you think about how this might apply to your business, to your data, to any sort of real world scenario. So here's the setup. There are hundreds of these examples that came out of this research, but here's the one that I like the most. Remember grade school level math. So Oliver picks 44 kiwis on Friday, then he picks 58 kiwis on Saturday. On Sunday, he picks double the number of kiwis he did on Friday. Now, this is all part of the normal GSM 8K test. But then the Apple researchers decided to add one little bit of additional information. And they did this over and over in many different ways, merely changing out the names or changing out the numbers or the kinds of things that were to be counted. And it would just throw these catastrophic errors. In this case, certain number of kiwis Friday, certain number on Saturday, an obscure number on Sunday. So can it reason and do some math? But the key that they added is, but 5 of them were a bit smaller than average. How many kiwis does Oliver have? O1 and Llama, the two most popular and latest closed source and open source models. In pink here, you can see double the number he picked on Friday, which is 2 times 44, 88 kiwis. However, on Sunday, 5 of these kiwis were smaller than average. This is the model talking to itself. So we need to subtract them from the total. So 88 minus 5 equals 83. And then you add that all together, you get 185 kiwis. That's wrong. And Llama did the exact same thing. And we see this fail in a number of these examples where the score drops from, let's say, the high 90s in terms of accuracy to 80s, 70s, and all the way down to 65% drop. I'm talking accurate to the 30s in some of the state-of-the-art, largest, most successful business models and the future of all software. Why is it making such a bizarre error? Well, it turns out reasoning is simply the function of understanding what cause and effect is. And systems that are doing correlational pattern matching might see millions and millions of correlations, but those correlations do not necessarily mean that the model has understood cause and effect. This is a very costly and dangerous way to get to causal reasoning and causal understanding. In this case, not understanding that the size of something, the size of kiwis shouldn't affect the number of them. And there are an endless number of these. I'll just show you a couple more things from the researchers themselves before we move on to the next step. This is Meredith. He's the team lead over at Apple. And he posted this on Twitter just a few weeks ago. Overall, we found no evidence of formal reasoning in language models, including all the top models. The behavior is better explained by sophisticated pattern matching. So fragile, in fact, that merely changing the names from Jennifer or Oliver, resulted in 10%, increase in failure rates. We can scale data, we can scale parameters with the size of the model, we can scale compute, or use better training data for these, including GPT-5, the next big model. But we believe this will result only in better pattern matchers, not necessarily better reasoners. This is a pretty big indictment. And it is a proof that these systems are incapable of doing actual reasoning. Why? Because reasoning to be accurate and effective is merely the ability to understand cause and effect. If you do it historically, sometimes we call that reasoning. If you do it forward in time, we call that planning. And this is what you need for agents. So can scaling data models or compute fundamentally solve this? We do not think so. And even though some of the later models perform a little bit better, understanding LLM's true reasoning capabilities is crucial for them to be able to be deployed in any real world scenario where accuracy and consistency are non-negotiable. AI safety, alignment, education, healthcare, obviously autonomous vehicles of any kind. Our findings emphasize the need for more robust evaluation methods, but essentially the headline here is developing models that move beyond pattern recognition to true logical reasoning is the next big challenge for AI. But at Versus, this is a challenge that we took on a couple of years ago, and it's one that we have already been able to achieve some significant results with. I'm going to explain to you today the difference. If the story and the plot is agents, if Microsoft is using OpenAI for their agents and Salesforce is using Llama for theirs and so on and so forth, trying to get reasoners first, this is a fail. They do not understand cause and effect. Why is this? It's because they're doing what you can think of as artificial learning, right? Biological intelligence, human intelligence, we learn a very specific way, and artificial intelligence doesn't do this at all. So what they do is they try to learn correlational based pattern matching, right? Off of large data sets that have repeated examples of the same data. So you say a million pictures of cats, then I know what a cat is, right? And so, but what are they trying to do? They're trying to model causal relationships. That's the whole point of downloading all the information on the web and hoping to get a model that can churn through that. But if all you have as a starting point is correlational data, then you're doing associative learning, not understanding how small things cause effects in other things. The sort of top-down brute force approach is the kind of fly in the ointment, right? This big data wave is the opposite of how biological intelligence. So it's correlative, not causal. And as a result, it leads to these kinds of unfixable gaps and inaccuracies in the model. And of course, we've used all the data, we're gathering all the chips, we're spinning up nuclear plants and talking about $100 billion data centers. And this scale is all you need approach is now achieving, diminishing returns for exponential costs. So there's an architectural flaw in this. How might we understand how the brain works well enough to be able to make one in software? Well, at Versus, we start by looking at the brain itself. Our chief scientist is Professor Carl Friston, the world-renowned neuroscientist who invented statistical parametric mapping, a lot of the underlying foundational brain imaging technologies. He's one of the most cited scientists in the world, not even just in neuroscience. And Carl Friston has developed an underlying mathematical model, much like Newton developed for physics and Einstein for relativity, but based on how neurons learn in the brain, and essentially how all biological intelligence is able to understand how to model information efficiently. It turns out, given the amount of energy you have is a huge function for how well you can think and learn and adapt. The essential ingredients for reasoning turn out to be a function of physics. And this is called active inference. So active inference is a mathematical framework for describing how systems learn cause and effect relationships in order to build an accurate model of the world or environment they need to operate in, which allows them to build a kind of model of that environment upon which they can then run hypotheticals, do predictions, reason about past events, reason about current states, and even reason about the future. What's amazing about active inference, though, as opposed to the kinds of inference we're seeing in today's systems, which are largely passive, kind of still pinging a very large model that's a black box that's already been trained but cannot continue to learn. Active inference, if I'm trying to learn cause and effect, I actually need to be able to see what effects I cause. Let's go back to agents for a second. That is what an agent must do. An agent is effectively a kind of cause that you want to produce a kind of effect. The desired effect, not another effect. These types of errors that we're seeing in large language models are causing a massive hole, sort of fragmented glass, if you will, within that entire model. Well, you never know where the error is going to come up because it just doesn't understand some basic cause and effect things. Active inference agents are able to model causal relationships. As a result, they can generalize to unknown scenarios, and they do not require massive amounts of data or compute to do that. How do we know this? Because the underlying science has already been validated. About 2023 in August, Professor Friston and some other colleagues of ours at University of Tokyo demonstrated how active inference was the self-organizing principle for how biological neural networks work in the brain. This was tested with real neurons, live neurons in petri dishes, where it could predict how learning, which neurons would update in what order within a petri dish, given a certain set of sensory inputs. So this is a way of demonstrating that the underlying mathematical model is able to represent the way that neurons work. And what we've done at Versus is take that underlying framework and apply that to software. And what you get is a new class of agents that are capable of learning faster, using fraction of the amount of data and compute. And we are at an inflection point as an organization where in the next couple of months, expect by the end of the year, internally, we're going to be able to demonstrate sufficient superior reasoning, planning, and adaptive learning in what's called the Atari test, where we will be challenging one of the largest AI models in the world known as AlphaZero, and even the hyper-efficient version of that. The approach that we're taking is with an intent of enabling a new kind of agent that doesn't use language comprehension as its basis for understanding the world. Language is a really powerful communication tool, but it's not how your brain encodes information. You're encoding smell and sight and taste and shapes and geometry and space-time interactions that are non-linear. It's not just about predicting the next token if you're going to survive in the world. You have to be able to model the world and operate in it. So we've been developing a full stack solution, which we call Genius, to enable better, cheaper, faster kinds of agents that can model the physical and social and emotional aspects that are required for real world agents, not just in software in accounting systems or for chatbots, but to be able to operate in cars and drones and robots and in the real world, and even be able to work together in ways that are also more efficient, wildly more efficient, and explainable. Why? Because they're able to model cause and effect. You're not just trying to pick out data out of a trillion parameters in a massive model. So this alternative to artificial learning is natural learning. And this is how you learn. This is how your children learn. This is what we see. Billions of years of evolution has shown that the way that systems learn in the real world is they learn from the bottom up, not from the top down. And it's all about learning cause and effect. So we understand this from neuroscience, we understand this from physics, but the ability for agents to be able to understand how small things, how you learn little pieces, those building blocks make up the next set of building blocks. Shapes become letters, letters become words, words become sentences, and so on and so forth. This allows you to model not just the objects themselves, but the relationships between them. Because you're modeling cause and effect, it's a sparse, lightweight model that doesn't require a $100 billion data center. In fact, could run on each one of 100 billion different IoT devices. This approach allows for causal understanding that agents themselves can test their understanding of the world. That's what cause and effect means. Not just a record of what causes and effects have occurred before, but how can I learn from my results? If I'm right, I want to reinforce that. If I'm wrong, I need to be able to correct it. This is a fundamentally different approach to developing AI agents that give us a baseline for knowing whether or not we can trust them to be autonomous enough to make decisions and take actions on our behalf. So to kind of connect the dots here, the underlying architecture for large language models, chatbots, generative AI are called artificial neural nets. These were originally developed in the 1950s. And we've basically been using the same architecture. Applied to the latest era of what's called deep learning, it's just add more compute, add more data, add more energy, and give it more cycles. Now, I want you to think about how you would want an agent to solve a problem for you in your business or in your life. If that problem is a kind of puzzle and you're not just giving it instructions or directions, because what's the point of giving instructions and directions to an autonomous car? I want it to figure it out and drive me to the location. In the world of artificial learning, what a brute force approach to solving a puzzle is taking every puzzle piece, learning the shape, and then trying every puzzle piece on every other puzzle piece. Now, obviously, you can have a system that never knows what's on the puzzle, that can brute force its way to solving a puzzle. Occasionally, and I've got a 4-year-old, so I've seen this, it might put a puzzle piece that doesn't really fit what we would see on top of the puzzle, but the shape can kind of be jammed in there. There's your 5 kiwis. And there are billions of these inside of the model. Puzzle pieces that are the right shape, but not the right piece on what's happening at the second layer of the puzzle. And that's what natural learning does in the underlying, what we call renormalized generative model that we use versus using for our genius agents. It's not just about the shape of each puzzle piece fitting together. And no human being solves a puzzle by trying to do one piece at a time and brute forcing it until it works. We actually group puzzle pieces together by color, by shape, by objects that we see. Today's AIs don't see anything but shapes. Nothing is on the puzzle. It doesn't understand the real world context. It just misses something like size and shape, right? Or the number of something and the size of something, as in the Kiwi examples. We have to have models that allow agents to be able to understand what's happening at that secondary level, whether that's human social context, whether that's understanding physical activities in the real world, or understanding space and time effectively. These are the critical ingredients. And so having an entirely new approach to how you develop agents that starts with the concept of agency and not just the concept of more data is fundamental to being able to do this right. And this gives us the ability to essentially have agents that learn causal reasoning, right? They understand cause and effect relationships, and this is what allows them to then reason, plan, and self-correct, because that is their main job. Active inferencing is trying to infer the causes and effects that lead to reasoning, which also allow explainability in these systems. And this approach inevitably allows for agents to dynamically adapt to unseen, unknown environments or situations, right? And generalize because they're learning the relationships between things and the structure of that, as opposed to just correlations and the number of times something happens. Now you can get agents that don't just learn what, but can learn why. To kind of connect the dots here and wrap this up for today, I want you to think about all of the different kinds of AI that we've developed over the period of the last few years. And I'm not going to make the case today that active inference-based agents, or what we're doing at Versus, is a wholesale replacement for all kinds of AI. There are kinds of AI that are very good for narrow tasks, certain kinds of skills, things that are highly repetitive, that you don't need high explainability for, it doesn't need to figure much out. But you need something that's missing in the entire AI space today. So if you imagine that we have pretty good vision systems, computer vision. We have pretty amazing robotic systems that have all kinds of motor functions, right? And we think of these as parts of the brain. We have IoT devices that can sense all types of information and measure that information in ways using artificial intelligence. Whether that's vision or sensory or motor functions, what we've added now is language comprehension. Large language model is not a world model. It's a language model. Language is an amazing representation of the world, but it is insufficient model of the world. And any argument is a pretty good example of this. The thing that's missing, if we want to use all those other pieces, is what we have in the prefrontal cortex, right? So we have this sensory AIs, and we have motor AIs, and we have language AIs, but what we're missing is the reasoning and planning functions that come in the prefrontal cortex. This is often called the executive functions. This is the part that does the orchestration, the reasoning, the planning, the learning, even emotional regulation, social cues, all of this happens. And it happens that if you're going to do reasoning, you have to do that in space and time. And if you're going to do planning, you have to understand space and time, right? This ability to understand those cause and effect dynamics, be able to run those simulations, that's the power of the frontal lobe, right? And that's what Versus is building with active inference agents. It can still use the language model for language. It can use a vision model for vision. It can use a motor-based model for robotics, whether that's a car or a humanoid robot or a toy. But the part that we're missing is the part that can do orchestration, navigation, and figure out how to reason about the world, make sense of the world, take decisions, and take actions, and even adapt and learn as it goes. And this is I think the missing ingredient. If we look at the context of we're essentially building a kind of brain or a kind of human, or sometimes called artificial general intelligence, this is the missing key ingredient, and this is what we're delivering. You can kind of see this in the market. The bubble feels ever present. I think the Apple paper was the emperor wears no clothes moment. I think that's going to reverberate through the industry. By this time next year, the industry will not even look like it does now. In the same way, it didn't look anything like this at the end of 2021, when then OpenAI came out, December 2022. So just in a 2-year period, we'll have seen this already kind of come and gone in terms of its peak, and replaced, I think, by more first principles based approaches that, if you think about the concept here, Versus has just been named as one of the emerging leaders by Gartner in what's called first principles AI, which they described as first principles approach bridges the gap between purely data-driven and physics-based modeling, enabling more reliable, more efficient, and more versatile, generalizable approaches to AI. And you see generative AI kind of coming over what's called the peak of inflated expectations on its way to the sad trough of disillusionment. And Versus is on its way up as I think, a valid contender in the field for a whole new approach. Incidentally, when we say something like first principles, what does Gartner mean? What do we mean? Well, first principles is understanding cause and effect, right? Going back to understanding how small things make bigger things and how those make bigger things and how that rolls up. Then you can track your way back down and really understand the structure of something. And this first principles-based approach is at the heart of what we're doing, not merely a generative approach based off lots of correlational pattern matching. And so we have a milestone coming up. You can think of this as kind of the Olympics of AI. But back in '96, was kind of a milestone moment in the AI. Gary Kasparov loses to Big Blue from IBM chess. 20 years later, this latest wave of deep learning AI beats Lee Sedol. This was called AlphaGo. It was later beaten by a model called AlphaZero. And then they said, that's the hardest board game there is. What about trying to learn and play dynamically, not just one game, but many different games, right? And Atari has emerged as the sort of state-of-the-art test. They took AlphaZero, they kind of tuned it up and said, okay, what if we could get this thing to learn to play a handful of games in 2 hours? What we've been able to demonstrate over the last few years is that we can get neurons to play Pong, the very first game in this test, from a petri dish using active inference. This is what some partners called cortical labs. Last year, we demonstrated that we could do that purely in software with a version of Pong, which we shared, that showed that we could beat efficient zero. And in the latest paper that we put out with those renormalized generative models that learn the different levels and layers of information, we were able to demonstrate the ability for the model to begin learning to play in 18 seconds. Now, just to give you some context here, what we're planning on doing, demonstrating internally within the next 2 months, probably by the end of this year, we're doing what we call Atari 10K. This would be our approach to beating efficient zero, the kind of big bad reinforcement, deep reinforcement learning model there is, with a tenth of the data. So 90% less data, not in 2 hours, but in roughly 12 minutes. Not using 4 GPUs, it's 4 NVIDIA A100s, but on a laptop, and with a model that's 100 to 1,000 times smaller. This would be kind of that, hopefully, Time Magazine moment that we saw when AlphaGo beat a human like Lee Sedol or Big Blue beat Gary Kasparov. And so we're looking into what's the right way to share this with the world, but this will be the key sort of agent-based benchmark. Why is this important? Because Atari games are largely irrelevant to most of the world. What this does is it shows how you can take an agent from scratch and it can learn reasoning, planning, and learning and adaptation in a handful of different environments that these games set up. And so these are analogs to the real world, which is often changing, often dynamic, has physics, has all kinds of complexity to it that the model has to learn. You could think of this as if the rest of the industry had been building, optimizing fuel injection on a 100-year-old, combustion engine architecture, Versus is the Tesla, and this is us beating a Porsche for the first time with the first world's, electric vehicle. In this case, it's a natural intelligence-based approach to AI that we think is, will should be able to demonstrate better, cheaper, faster, and safer. So to conclude, we talked about Bill Gates and others saying that agents are the key. This is the new kind of app, but instead of it being an app that software developers give instructions, it's something you give goals to and it figures it out by itself. In many ways, this is the ultimate vision of both technology and software. All of our sci-fi stories have arrived at some version of this. Bill Gates talks about this not only changing how we're going to interact with computers, but how this is going to change how we interact with software. But I think if it's clear, if anything is clear, it's going to change how we interact with the world. It will become the interface to all of the interactions and be the key mediator, ensuring that we can trust these systems to make decisions, to be autonomous, is only going to be a function of being able to know that they understand cause and effect, that it can be modeled in a way that's human interpretable and auditable, that it can adapt and learn and self-correct as it goes, and that it's efficient enough to be able to operate not just in one giant $100 billion or $1 trillion data center, but on the laptop. I believe that the work we're doing at Versus is equivalent to the microprocessor moment for computing, where everyone thought back in the late 70s and early 80s that supercomputers, maybe we'll have 3 or 4 of these things and everyone will connect to it in the world. It turned out the microprocessor that gave the power of computing to everybody, put it in their hands, on their desktop, in our pockets, and now everywhere else has just been the setup for a new kind of software that's going to enable agency at scale. And I would agree with the last thing that Mr. Gates said here, which is that there's a significant chance that this future AI winner will not be one of the big players. In fact, will be a startup. So thank you so much for the opportunity to speak with you today. It's been a real pleasure to share.
Well, thank you, Gabriel. Certainly a very provocative set of comments here. I have to admit, when I came to COSM this year, I didn't think I'd learn so much about Broca's area, but knowledge from an unexpected source. So at this point, I'm going to actually ask Greg Meredith to come on up to the stage here. Greg is a longtime, multi-decade technologist who has been working on distributed systems and communications layers and data access patterns across many different kinds of architectures, and has. I'd like him to sort of introduce what he's doing working on at Firefly, and then also any comments you may have with respect to the comments that Gabriel just shared.
Well, thanks, Bob, and I want to thank George and Steve for inviting me to engage with this panel, and to thank all of you for attending today. Originally, the way we'd structure the panel was I would respond to Gabriel, and so what I want to talk about turns out to be a response that I think fits very well. So I think Gabriel and I wholeheartedly agree, but we're coming at it from completely different perspectives. But one thing that we absolutely agree on is going back to first principles. And so I want to talk to you a little bit about some first principles that you may have never heard of before. And so what I'd like you to do, I'm sure probably everyone in this room has heard of the simulation hypothesis, that we're all living in a simulation. Well, I want you to forget the simulation hypothesis, and I would like you to enter into the world of bisimulation theorems. Right? So I'm going to explain a little bit about what that means. You may have recalled at the top of Gabriel's talk, he talked about getting to planetary scale with these kinds of intelligence agents. And I think in general, humanity is terrible at scaling. And why is it terrible at scaling? Well, because the consequences of the way we scale end up being fairly disastrous. So I tend to ask, how does nature scale? And one of the ways that nature scales is through composition. So I'm just going to plant that like a seed, from a plant, from the natural world into your minds, and then I'm going to return to that idea towards the end of my response to Gabriel. And so having planted that seed, keep that in the back of your mind, ready to bloom at some point. And now I want to turn to a couple of practical queries. These are queries which currently are not statable even in existing search and storage mechanisms, including AI-based search and storage mechanisms. So the first one is, find me all the small molecules from this repository, say Swiss Prot or one of the other chemistry or bio repositories, such that when I drop it into this cell signaling regime, in a certain concentration, the cell signaling regime never reaches a particular state. Now, why is that an interesting query to be able to articulate? Because the English translation is, find me a small molecule-based cure. Let me provide another query. Whoops, there we go. Let me provide another query that would be of interest. So find me all the, so using this collection of CAD-based repositories that articulate the structure of aircraft, find me all the wires running from the nose of the aircraft passing through the midsection where aircraft flex that are likely to, that undergo a twist. So the translation of that query in English is, find me likely sources of electrical shorts. Now, again, in today's systems, you can't write those queries down. It turns out, however, there's an algorithm, in fact, there's a family of algorithms that allow us to generate query languages and query processors that process those kinds of queries. They can be generated from the domain languages where you naturally find these kinds of questions. So in particular, the first one can be generated from the language of chemistry, and the second one can be generated from geometric algebra, also known as Clifford algebra. So the interesting point about the kinds of query languages that this algorithm generates is that the queries are perfectly explainable. We can find cause and effect style reasoning that goes into the processing of those queries. Now you're wondering, where does this algorithm arise from? Probably. So the algorithm arises from a notion from theoretical computer science that you've probably never heard of by the name it's given in that community, and that name is Bisimulation. But you know it by another slogan, and that slogan is, anything you can do, I can do. Right? And if we have time, and the other talk ran a bit over, so we probably won't have time to get to it, but if we have time, I'll address what happens if you add better. Anything you can do, I can do better at the end of that phrase. Now, what's interesting about this principle is that it classifies all computational behavior. That's really important. Right, so the mathematicians or mathematically adjacent in the audience probably remember what a big deal it was a couple of decades ago when all finite simple groups were classified. Right, that was a huge deal because in some sense it meant we understood all the mechanics underlying notions of certain kinds of symmetry. Right, so Bisimulation does this for all computational behavior. Now, what does this have to do with AI? So I want to argue that AI is a misnomer. And again, very much in agreement with what Gabriel was saying, but coming at it from a different perspective. So he's motivated by biological systems, and I resonate with that, but I also want to understand it in terms of compute. Right, because I believe that right now with the premise underlying the AI industry is that there's at least a class of practical, useful aspects of human intelligence that can be represented as computation. So even in Gabriel's presentation, ultimately he's rendering what he's doing in software, right? So he's still bought into the idea that when we're doing AI, we're reducing at least certain aspects of and I would argue human intelligence, to computation. And not just any computation, because there's all kinds of computations we can imagine, right? But we're talking about computation that can be rendered on machines that we can produce and manipulate at scale. Okay, so the right word is computational intelligence, or CI, and CI presupposes that a particular world of intelligent actors, for example, the kinds of things that Gabriel was talking about as agents, are live inside the world of computations. Now, what Bisimulation says is everything in that world can be completely classified. That means that any denizens of that world, for example, an algorithm that can learn, can also learn no finer classification of phenomena than Bisimulation equivalence classes. So if you come up with some algorithm that can classify things in the world, it's actually never classifying things in the world. It's only ever classifying computational representations. And those things can, the finest classification of those phenomena is in terms of Bisimulation. So these facts are at the heart of this algorithm that I mentioned, and it's at the heart of query engines that Firefly is building. Actually, we're building sort of a meta query engine that allows you to generate those query engines at scale. Now, how do we get to planetary scale? So I want to argue that the natural world scales through composition. Now, so what do I mean by that? So in terms of the standard model, which we all know is probably wrong, but it's the best we've got, atoms are made of quarks, leptons, and bosons. And molecules are made of atoms, and proteins are made of molecules, cells are made of proteins, organisms are made of cells, populations are made of organisms, right? So the thing to take away from this is that composition is really the bedrock of a proposition that is at the heart of Western science, right? So the view of Western science as taking a reductive view of the world is really backwards. What Western science is really saying is that the natural world is built through composition, right? We compose cells to make organisms. And so the sense intelligence is a naturally occurring phenomena, right? Right? We are all biological organisms in this room. Shouldn't we expect that an effective account of intelligence should be deeply compositional? So what Bisimulation does is it classifies all computational behavior because it exposes the deep compositional structure of computation, right? So computation actually has building blocks, and Bisimulation exposes those building blocks in terms of this principle: anything you can do, I can do. And that is how we begin the process of scaling. So I've tried to keep it very short rather than long. So I'd like to thank you again for your attention, and if there's time, to open it up for questions.
Yeah, I'd like to open it to questions. One of the things that's been fascinating for me, though, over the course of thinking back over the last few years of COSM, is you sort of think about the impact of AI almost when we first started having some of these conversations is about kind of the machines. And this year is much more about sort of that recognition that actually the machine is reflecting kind of the human brain and the ways in which the patterns of the human brain understand. I suspect that while we've been talking about reasoning, I suspect next year's COSMs and the COSMs after that will be about reasoning, judgment, and maybe even morality. Because the problems that you actually end up with in a world where it's just the machine separated from those other elements is that you don't have well-formed choices. You get answers, not well-formed choices. It'll be interesting to see how this sort of conversation evolves over the coming years. With that, I'd like to see if there are any questions in the audience. Sure. Gabriel, do you have any comments to respond to Gregory or to add there?
Yes. Can you guys hear me okay? I shifted to AirPods.
You're good.
Can you? Yeah, so I'm not familiar with bisimulation theory, but I have some assumptions. So I want to respond to areas where I think there's some overlaps, where I think there's some gaps, and then some questions to make better sense of it. So first of all, when we started Versus, we started from the perspective of spatial computing and cognitive computing as a function of space-time understanding. And so we began by developing a language called hyperspatial modeling language, which was a way of, essentially, how can you get computers to understand what all those different sensory inputs might be and how they might be fused together to have real-world coherent digital twins, right? How could they understand the physical activities, objects, states, properties, but also social ones, like you just mentioned, ethics, morals, which turn out have many physical corollaries, right? We spent several years developing that. We've been working with the IEEE for the last 4 years. It's just been voted in as a standard for AI interoperability, explainability, and AI governance. I expect that to be ratified in early Q1 of next year. And I, felt pretty proud of that. No one had ever built these sort of ontological frameworks or arguably epistemological frameworks that were very all-encompassing, because we saw that everyone would take sort of piecemeal industry-specific or technology-specific approaches. And so amazing group of people from around the world that worked on that. About 3 years ago, I was introduced to Carl Friston through a professor at MIT. And he was like, you gotta talk to Professor Friston, who I'd never heard of, because a lot of the things that you're saying are very similar. Like Gregory just mentioned, the idea that things are compositional, that they're hierarchical sort of nested structures, right? Meaning things are made up of other things. What we often refer to as holonic, but our peers often just refer to as nested. These were very similar. The idea of these sort of structures that you were talking about as being representations of aspects or attributes of the world was very similar. And I remember the moment where Professor Friston, I said, look, what do you think we're not modeling here? Because I haven't found anyone in years that could come up with something that we can't model, whether it's at the physics level, whether it's materials, whether it's light refraction, like anything that you could describe, we should be able to describe in HSML. And he said, how about probability? I'm like, what do you mean? And he said, well, you can model all these things, but you think things, I'm paraphrasing, he's British and he says it much more interestingly. He says, you think those things are what they are where they are, and they're doing what you think they're doing, but they only probably are. With respect to what matters from a representation perspective, given a decision you need to make. And that blew my mind. And so the notion that you need to be able to have representations of the world that if they're to be like, if they are similar to how the brain represents information, they're dynamic, they're probabilistic, they're not fixed. There are trends and there are structures that are common, hence being able to say something is chemistry or something is biology or something is an apple or something is banana. Those features and states are have some degree of stability. But it turns out, everything is made up of parts, but all those parts and all those relationships are constantly changing dynamic, and you have to be able to model that part. And so that's the thing that in any representational structure, and I certainly came to that, realization after working with Carl for the last few years, and genuinely trying to understand, not from a computational perspective, which ultimately to be useful, I agree, is what we have to do and what we're doing. But we have to understand how does nature do it first. I mean, it's the best lab in the world. So that's my comment. I think that Gregory's absolutely correct. We are very aligned, and I think we're approaching it from different angles that are also complementary. But I think we're talking about structure, and the process of intelligence is not limited to structure or sort of specific sort of representations, but probabilistic. So my sense is that, and this is where I'd love to learn more, bisimulation is a kind of semiotic approach to signs and symbols and representations, which I would agree you can represent anything. It turns out representing probability is its own kind of challenge, which is usually a sort of Bayesian model. And this is what free energy modeling gives you the framework to do. And as a result, that was how we ended up at active inference. But I believe we're fellow travelers on a very similar journey. And I do think that next year we will be talking about the impacts of reasoning or the ethics of reasoning. I think those are my initial thoughts.
If it's all right for me to respond, first of all, thank you for that. I wanted to just re-emphasize what I said at the very beginning. Bisimulation is not about structure; it's about behavior. The principle is anything you can do, I can do. Right, so it's all about behavior, and in particular, it's about computational behavior. What's very interesting is that Jonathan Worrell, a noted researcher in computer science, and I have shown that for any given system where we have a natural notion of bisimulation, we can not only automatically derive a stochastic version, which includes probability, but that's just one norm-based probability, right? So that's like the coin flipping kind of stuff. But we can also automatically derive two norm probabilities. That's quantum stuff. So for any given logical notion of computation, we can auto-derive a corresponding stochastic version and a quantum version. So that's why this approach is starting to, for me, make me feel a little bit more confident, a little bit more comfortable, because we're, as you suggested, Gabriel, you have to be able to address uncertainty in the form of probability, but you also have to be able to address uncertainty in the sense of quantum mechanics, which is a different kind of uncertainty, fundamentally different kind of uncertainty. So great conversation. I'd love to talk to you more.
It sounds like we have a conversation that has to happen after this. So first of all, thank you to both Greg and to Gabriel. Wonderful conversation. I appreciate that. We are getting the Grim Reaper red sign here, so I think it's time for us to head off. Thank you.
Thank you.